Okay, then let's continue. The last bit in terms of EEG source analysis is on distributed source reconstruction. Again, that uses the same dipole model as we have seen previously, but it doesn't have the problem of trying to fit the dipole location because it puts dipoles everywhere. In the brain, that means on a grid of, if you want to call them voxels, that you pre-specify. So in this case, of course, depending on the resolution, you can easily imagine that there are there are many more parameters than data points, meaning that for each dipole you have 3 parameters, namely the 3 moments, and you only have at a given time point, let's say 64 values. So that would be, if you have like 1,000 dipoles, you have 3,000 parameters to estimate, but you only have 64 values from to estimate them. And this is of course ill-defined, and you don't have unique solutions. So many different dipole patterns can explain a certain data. So one needs to introduce constraints, and then the EEG source reconstruction literature on distributed source reconstruction is mainly concerned with the question of which constraints to introduce. And this then leads to the fact that the distributed source approaches are classified actually according to their constraints. One thing is that you can do is, of course, ignore all white matter and subcortical aspects, which you might not actually detect in EEG anyway, and use cortical constraint solutions. So you only put dipoles on the gray matter. So, for example, by coming up with a cortical mesh in which you then place dipoles. That's kind of biologically informed, and non-biologically informed constraint would be to have the constraint that the overall dipole activation is minimal. That's what's called minimum norm solution, and that's a typical regularization or constraint technique that is used in many of these ill-defined problems. Another thing that one can do is a depth-weighted minimum norm, which arises from the idea that the overall dipole activation is a little bit biases towards superficial sources, and so the minimum norm is more stringently applied at the cortex level. And another thing that you can do is to maximize the smoothness, now not in terms of random fields or anything, but in terms of varying over space of the, I mean, it's the same kind of idea, but it's not, it doesn't use the random field model. And this leads to what is known as low resolution electromagnetic tomography, or LORETA. All these, they have many names, and then people usually say, I'm doing LORETA on my EEG. They don't say, I do a distributed source reconstruction in which I put in the constraint that the activity is smooth, but they say, let's do LORETA. And there are really many variants, and they have all funny names, like music, e-music, rap music, I think, it's, because they are usually these acronyms that then...
So which one does LORETA refer to?
Low resolution electromagnetic tomography, that's LORETA. Yeah, these, the variants with the funny names, they are actually not on the slide, but there are many. Because that's what engineers do, and they then always come up with one that is a little better than another one. So, yeah, this is how one can imagine this here with a caudally constrained dipoles. So here you put voxels, they have dipoles, and there's something about there. Looking into my head text here, whether there was something important about this. No. Yeah, so the idea is that there are these sources, and if they are active, then depending on their specific forward solution for at this location, superimpose at the electrode levels. So it's just a picture. As for the model, that's now rewritten the dipole model that we've seen previously for the case of distributed source data. Now the difference is that the lead field matrix actually becomes much more high dimensional in its columns. So although the dipole model is the same for the equivalent current dipole models and for the source reconstruction models, the difference is of course that in the distributed source model, one looks at a collection of dipoles. Yeah? So one has computed the lead field matrix for all number of locations. So I call that here NV, like voxels. So you can think of voxels. And for each voxel, you have now these 3 columns, like we had for before, only for one dipole / one voxel. We only had a 3 column matrix. Yeah, but besides that, no, not only of course now also the moments are to be evaluated for each dipole, yeah, and this is where the many parameters come in. So you want to, so you know the maybe I should change my pointer here. Hello. The pointer is broken. That's great. See the laser pointer, the batteries are low for the laser pointer. So I can use, I can't see that, but I can use my mouse, but I cannot use the laser pointer. It's broken. Pen still works. Life is not easy in the first world. The electric laser pointer is broken. A little bit small, but at least you have some movement there. So the difference or the parameters that make this whole thing ill-defined is that you have that you want to estimate the moments for all dipoles at all these locations, yeah, and so you have 3 times the number of locations, the number of voxels that you need to estimate. And the problem is, like I said previously, that the number of voxels, number of dipoles, that you have many more than you have data points, and this leads to a linear equation system with more unknowns, which are these x's here, than knowns. And of course, if you have more unknowns than knowns, then you can do some theory of linear algebra of linear equation systems, or you can just intuitively think if you want to know 1000 values, but you only get 3 from which to determine them, then you might have many ways to do that. And hence you have to select constraints, and these are the ones that we discussed. So you select specific x's. So one example is that you always add a regularization term to your, so when you're trying to, so you have an objective function and you try to minimize the deviation between your prediction based on a certain setting of x from the data y, and then you try to minimize this prediction while at the same time also minimizing the norm, so the overall activity of the dipoles. Yeah, I think the next one, so this is the kind of formal level that we're pushing that to. The next 2, this shows a little bit of a example of what you then get. So if you put in smoothness constraints that assume that neighboring voxels show similar activity, your solutions, so your activity will look like this, so they will look fairly smooth. If you put in sparsity constraints, then you kind of try to bias the distributed source reconstruction to what dipole model would do, and then you would have much sparser and of course more regionally specific activities. So here you see some solutions for this from a sparseness constraint. So the question, so this is already the end of distributed source reconstruction. Just because I can see what I have on the slide and I'm just trying to prepare for that. So the bottom line is, yes, you can project EEG activity from the electrode level to the brain, and hence say this brain region is active in this ERP experiment and this brain region is not active. You have to, solve the forward problem, which you usually don't deal much with. You have to use the inverse problem, and there are these two approaches: the current dipole modeling and distributed source reconstruction, which are commonly used. The question is then, of course, always how good is that? How exact is that? Can I trust that? And this is not that easy to answer. So one thing is, of course, that you ideally want, if you do simulations, that your reconstruction method is error-free in simulation, so that you can recover what you simulated. Although this already makes a lot of work, or creates a lot of work, because especially if you think about that you want to do this through the whole brain, then you have many simulations to do. You can find a little bit, so I use frequency domain Loretta in one of these visual dataset papers, and in the supplementary, I think, of this 2011 paper, I looked a little bit into the exactness of Loretta for what I was aiming at, because I had to reprogram Loretta a little bit to make it work under the conditions that I wanted to make it work. So that's one thing, but then the other thing is for real data and for the real brain, how good it is really hard to answer, because first of all, you would have, if you want to, you don't have a ground truth like always with real data. So what you ideally would want is to have a physical model that is somehow like the brain, but like in a 3D and constructed, where you then can actually turn on some activity at pre-specified locations and record EEG and see how good that is. And the rest is then, if you're using real data, this kind of face validity. So if your method in simulations is okay, and then you apply it to EEG activity, for example, from primary somatosensory stimulation, and you recover primary somatosensory cortex, then you would say, well, this is good. I think so. The comments that follow here, they are a little bit in the discussion with Luck. So if you read the Luck book, he's very skeptical of the whole thing. I think he's a psychologist by background, and so I'm not that skeptical of the whole thing, because I'm as skeptical of the whole thing as I am of any science, quantitative science, because it's a typical quantitative data modeling problem where there is not the overall best method. All solutions depend on the model assumptions. That's always the case. I mean, these are data models, and of course, what you put in terms of your assumptions about conductivity in the forward problem, of course, determines what you get in terms of your activations from the EEG data. And also here, like with all things, like pre-processing, as we discussed last time, informed use is advisable. So if you have very small activity in your consciousness area that you cannot clearly dissociate from noise, and it's highly dependent of whether you use Loretta or some other source reconstruction model, then maybe don't believe it that much. If you have visually evoked potential activity and you see it using Loretta and other methods or dipole methods in visual cortex, then maybe believe it a little bit more. And somebody must have said that this is weird. So I say this is not weird, this is science. I don't know what this actually belongs to. But yeah, I think the reasoning behind is that especially psychologists that then in this, or it's the same story for DCM, where it becomes apparent that things depend on models and you just not only compute descriptive statistics, where of course you only compute descriptive statistics because you have models in your head that you don't talk about. That's when there's always some kind of frictions. I don't believe that, but it's just normal, so don't worry. Questions about source reconstruction? No, everybody's doing something else anyway. Good. Then we have quite some time to start with frequency analysis, which are also very interesting. So that was basically projecting EEG data into the skull, into the brain, into the skull. And now we are looking at projecting EEG data into what's called frequency space. So who of you knows how do I ask it? Who of you knows what Fourier analysis is?
Conceptually?
Conceptually, that's what I mean. So what is Fourier analysis for you conceptually?
You try to decompose some complex waves into more simple, I'm not sure if it's sine waves or just simple waves, so that you can say, I can compose this difficult complex wave based on different frequencies, right? Yeah,
essentially that's it. Lena next to you wondered whether by complex she means complex numbers or she means but this is what always once you go into Fourier analysis you deal with complex numbers usually, but that's complex in the sense of topographically complex or whatever. Yes, exactly, that's it. And this is also what we are looking at. So so basically you try to decompose a signal, like you said, into sine and cosine waves, which already of different frequencies, which already then led in the last scan core to a discussion whether that's sensible. And of course it's not sensible because you can have many different kinds of functions on which you want to project data, so you don't need to use sines and cosines, but of course sines and cosines come with a frequency associated to them, and then there is, I don't know, one can quite easily create neural oscillators, so one can write down differential equation systems that oscillate. And I think this motivates, I actually don't know what motivates people to do frequency analysis. Honestly, I don't know. They do it, they find differences, then they report these differences as significant, so there's a change in alpha band. And then it's, and it's like, there's a change in alpha band. Anyway, so because somehow there's the belief that, I don't know why people do frequency analysis, but I will tell you what frequency analysis are. I really don't understand why people love frequency analysis so much. I mean, it's a data feature. I can see that, of course. Looking at potential deflections is also a data feature, so it's not something that is different, but it's not biologically more meaningful. This is the point I'm trying to make, that per se, seeing changes in frequency spectrum of something is not that this is neural activity, and the time domain is not neural activity. It's just a a different domain of where you look at it, and you would have to establish some neurobiologically plausible oscillating model to underfeed all this frequency domain business. Good. So that said, in a little bit wired mode, what we want to talk about in frequency analysis are first time domain versus frequency domain, which essentially refers to the intuition that we just discussed. Then a little bit about filters, because one can view them as acting also in the frequency domain. And then finally talking about time frequency analysis as you see them often in EEG. So the basic idea of the whole thing is that what we already discussed, that you have a signal in the time domain. So on the x-axis here you have time, and then you have, for example, an ERP of a single electrode in this case, because there's a single line that changes over time. And now you want to represent this signal in frequency space, and we will see many more visualizations of this, but the fundamental idea is that you use sine and cosine functions of varying frequencies, so highly oscillating and not that much oscillating, and instead of representing the signal over time, you represent the signal in this time window, so from here to here. You can see that roughly. Let's see whether my laser pointer is working again. Maybe I can actually, should work if I get my laser pointer back. Oh, there it is. You represent this whole time window, so essentially the average of this time domain signal in frequency space. So there is no notion of time in this plot anymore. There's a notion of frequency content and a notion of frequency, so higher frequency here, lower frequency there, and the content of this thing. But this doesn't say at which time point. Yeah? So that's standard Fourier analysis. So the next couple of slides have a little bit on the underlying math. As I said, I think I will teach Fourier analysis in the winter term. I haven't taught that for 2 years or so now, and I should look into it again and also create some videos on Fourier analysis. So the Fourier analysis, actually the term Fourier analysis is actually a broad term. So originally, Fourier analysis actually didn't derive from this question that somebody had an electrical signal and wanted to do a frequency decomposition, but it originated in partial differential equations and the question of whether you can represent a boundary condition in terms of the sum of sines and cosines. So that was Fourier's original motivation, so in heat conduction problems. And then there was quite some mathematics that tried to show that you can write any function in terms of these Fourier series, and then only with actually the advent of the fast Fourier transform algorithm. Fourier transforms are something slightly different than Fourier series. With the advent of the fast Fourier transform algorithm, actually, it was really easy to do these kind of frequency decompositions. And that's then when people used that, but Fourier analysis is much older than that. So the math, as I said, you can see in the winter term if you attend the course again, or maybe then watch the videos. It relates, so the aim is really to represent signals by means of cosine and sine waves. But the standard cosine and sine, as they are plotted here and given also in the series form, so this is series meaning an infinite sum, they of course don't allow for representing different frequencies. So the sine function does not have different frequencies. That has it has a frequency of what's the frequency, and depends on how you express it, but it does one whole turn in once every cycle, so 2 pi, so that would be no, I don't want to go into that right now. So it has one frequency, namely it repeats itself every 2 pi, same for the cosine. So when you talk about these frequencies in terms of Fourier analysis, what you actually have in mind are these generalized sine and cosine functions, which obtain frequency parameters. So you put in another multiple in there, so into the sine function or the cosine function, which you then can do in 2 ways. Using either this omega parameterization, which you multiply by 2 pi, then you get rid of this 2 pi, and you get you can talk more about what you are familiar with, that you have 1 repeat per period. So that would be 1 repeat every 2, but it's actually the inverse, and so on. So this is actually the math that I didn't want to talk about here. But the important thing is that you need generalized sine and cosine functions, which vary in their frequencies and can actually also are also multiplied, so that they can have different amplitudes. And then if you have these generalized sine and cosine functions, you can do what actually we said in the very beginning about the intuition, although we're doing it here the other way around. So if you have one sine function that looks like this, you have a cosine function like this, a sine function that looks like this, and a cosine function like this, and you add them together in terms of what would be a finite Fourier series, you can recreate signals that look kind of like signals of interest. Yeah. So here this shows for another example. So the stuff here on the bottom, that would be what you would call actually your observed EEG. And these are made up out of these generalized sine and cosine functions. Of course, what you want to do in terms of frequency analysis and Fourier transforms is to go back from this observed signal to the respective amplitudes of these components. So this is shown here again in terms of the luck book. So here, what is shown here is actually how you trying to recreate a square wave, which is kind of a special case already for the whole thing, by adding sine waves of given frequencies, and then by adding these 4 here, creating something that looks more and more like the square wave. I think you can actually not recreate the square wave completely. Can you, Lena? Can you create the square wave? Does it work? I'm not sure right now. I don't think it really works. There's a kind of a limit. But so the idea is again the same, so that you use these varying frequencies with different amplitudes to create a signal that you that looks like a signal that you observe. So the next slide shows the whole thing a little bit more formally to make things clearer. So the signals that are actually of interest are functions, univariate real valued functions, and the fundamental assumption is that these are periodic. The nice thing is if you apply this to real data, the period can just be your whole observation interval, so you don't have to actually have a periodic signal. You can just concatenate signals that you have observed again and again behind each other, so then it's period. And so that's kind of the signal. And then you can certain functions under some constraints can be re-expressed in terms of the Fourier series, which is this infinite sum. And the interesting thing about a Fourier series is that there are actually 3 different forms. And this is, especially if you're starting with this is quite confusing, because you always come with this intuition, and that's completely fine, that you think about frequencies in terms of sine and cosine, or better, generalized sine and cosine functions. Yeah? So that you have cosines and sines of different frequencies. These frequencies are here these k's, and you change the k, so you have different frequencies multiplied by this omega 0. You change the frequencies, you have low and high frequency content, you have the amplitudes. The amplitudes you can actually compute based on your function by integrating these things. So, as I said, in the winter term we will go over how actually to derive this. But it's fairly intuitive, yeah? So you have an amplitude factor, you have your cosines, you have your frequencies, and you try to represent a signal. Now, once you, I don't know, do a fast Fourier transform using MATLAB, or talk to Bernhard Spitzer or anyone who does frequency analysis, you will enter the fact that people often express the Fourier series actually in using complex numbers, which all is due to the fact that you have this Euler identity that or have Euler identities which bring together how you can express sines and cosines as complex exponentials, and then actually your nice intuition from the frequency business and cosine sine is somehow lost in dealing with these complex numbers. And then even worse, you have this polar form, which then you can look at in terms of your in a two-dimensional plane. So the bottom line from this slide is more as a teaser that you are very motivated to attend the winter term, because you know that there are these equations and you really want to know what they mean. The bottom line is that to get the coefficients, so the frequency powers, if you want, for the real form, what you need is the signal and computing some integrals. If you have these, so this A0, AK, and BK, you can compute, if you want, the complex form and its corresponding coefficients. So you can equivalently go from here to there or from there to here. Same for the polar form. So that means that if you somehow have now a complex number representation of the Fourier series, you're not completely in a different world, and MATLAB is not doing something wrong if it gives you complex numbers for your fast Fourier transform. You can, if you know the right conversion formulas, always bring that back to cosine and sine functions and their corresponding frequencies. Yeah. Good. So this is a teaser for the winter term. Good. I think we will be able to do filters. Yeah?
Are you going to talk about wavelets?
No. We will talk about time frequency analysis. Maybe we actually should stop here. So you can answer a couple of questions and then stop and do filters and time frequency next. So wavelets are different basis functions from my perspective on which you can project data. And of course what you're trying to do is to adjust, in terms of for wavelets, you're trying to adjust the size of your window over which you evaluate the wavelet according to the frequency of your wavelet, so that you estimate low frequency stuff not on too little data. But wavelet, it's the same logic, but instead of sines and cosines, you use different functions for good reasons. But why are you interested in wavelets?
I think we're writing a paper and Jacob's question, and then I was just wondering what was the difference to Fourier.
The difference is essentially that in normal Fourier analysis, when you look at, if you do, based on this, actually do a Fourier analysis, you get a frequency power spectrum, and you get the same thing from wavelets, but computed a little bit better, essentially, a little bit fancier. But the end result is the same, especially, I mean, we have to go over time frequency analysis because this takes a little bit of time because they're different forms. But essentially, you can view windowed Fourier analysis, so doing this only for a time window here, and then looking at how the frequency content changes over time as the same thing as wavelet analysis. But if you really go into the math, then there are many more interesting things. But we are not really going into the math. Come on. We are neuroimaging people. We have to write papers. We have to get great results so that we get great funding. We cannot really deal with these little details. It's just, we need a job after all. Good. There was another question.
Yeah, does Fourier analysis have the same issues as the source analysis, and that there's not always a unique solution, or is that different?
Yeah, that's a broad topic. No, essentially it's not the same, so it's not over-parameterized. Usually, especially if you're, because you will, so for example, if you're doing fast Fourier transform algorithm, which is also is in my book and also in MATLAB and hopefully in the winter semester, you actually limit the frequency resolution to the number of samples that you have, which means that you're not inducing a situation where you have more parameters essentially than you have data to estimate them from. So in general, the Fourier transform is not an ill-defined problem. But then, of course, you can do modifications so that you get ill-defined problems. But in general, not. In general, it's really there's a unique representation of what you have.
And is that true going both directions, both from
yeah.
the signal?
Yeah, it looks. I mean, yeah. So one direction definitely. I mean, this is if you this is also not where you can have ill-defined things. So if you go from the decomposed to the composed, then you just get what you sum together. So there you cannot have really an ill-defined question. The question is always when you have only one thing and you want multiple things from it, that there might be different things added together that give you the same thing. But we will talk more actually then next time talking about how this is applied to EEG. This was then just a taste, but I don't want to rush that now in the last 5 minutes. Any questions? More questions? No. Good. So then I think we have one more session to go on EEG. So next week then in the first session we do EEG frequency analysis after briefly talking about frequency analysis today, and then in the next hour we can start analyzing EEG and fMRI, starting with fMRI using MATLAB and SPM. Good, then have fun and see you, or whatever I say at the end.